Hi friends, we are going into the class 1 of module 3. This module 3 is a continuation of alternating current, and in this class we are going to study about what is phase. Okay, so what is meant by phase? The phase of an alternating quantity is the fractional part of time period through which the quantity has advanced from a selected zero position. Okay, so how much the AC quantity has advanced from the zero position? Zero position means there is a reference. Okay, so in this case, to understand it more, we are going through three waveforms as shown, and we are taking a reference axis or zero position is being taken, and according to the zero position, we are going to analyze what is the phase of the AC quantity. Let us go through the first one. You can see this is the reference axis or the selected zero position. Okay, and how much the AC quantity has advanced from the zero position is known as the phase. So here you can see the AC quantity has already started from the zero position itself. So there is no advancement or there is no lagging behind. So we can call this one as A is equal to, or we can represent this waveform as A is equal to A sine omega t, where small letter a shows the instantaneous value, capital letter A is the maximum value. Just as V is equal to Vm sine omega t, we are just taking an AC quantity A. So A is equal to A sine omega t. Let's go to the second one, second waveform. You can see in the second waveform, this is the zero position. Okay, but the wave has started a little bit after the reference axis or the zero position. Or you can see that there is an angle phi by which it is starting, after which it is being started. Okay, such a waveform is normally represented as A is equal to Am sine omega t minus phi. A sine omega t minus phi. I forgot to put the bracket here. Omega t minus phi should be put in a bracket. Sine of omega t minus phi. Okay, and similarly, let's go to the third one. In the third one, you can see this is the selected zero position, and before 5 degrees, what has happened? The AC quantity has been started. So this is the point, or it is advanced from the before the reference axis itself, it has been started. So such a waveform can be represented as A is equal to A sine omega t plus phi. Here also there is a bracket. Okay, so that is regarding the three types of waveforms with reference, with the help of reference quantity, how can we mention the or represent its equation. So this angle phi is known as the phase of an AC quantity. So in this case, we can say the phi value is equal to 0. Why? Because it is already starting from the zero position. In this case, the phase value is phi. And in this case also, the phase value is phi. And we will be studying how to represent these two phase values. How should we represent this one and this one? How can we identify whether it is going after the reference, coming after the reference axis, or it is coming before the reference axis? We will be studying further. So next one is what is meant by phase difference. What is meant by phase difference? When two alternating quantities of same frequency have different zero points, as mentioned before, they are said to have a phase difference. If two quantities having same frequency are being compared, and if they are having different zero points, then we have to say that there is a phase difference between them. Okay, and it is represented by the letter phi, and it is measured in radians or degrees. So, according to the comparison, there are three types of phase differences. First one is in phase, second one is lag, and third one is lead. In phase is one type, and second type is actually out of phase, in which there are two, that is lagging and leading. We are going further into each of them. First one, we are going into what is meant by in phase quantity. So what is meant by an in phase quantity? If both AC quantities of same frequency have same zero point, if both the AC quantities are having, which are being compared, if both of them are having same 0 point, then we can call it as in phase. They are in same phase. We can say that the two quantities are in same phase, or we use the term in phase here. If both quantities having same frequency have their same 0 point, then we can say that two alternating quantities are in same phase or in phase. Okay, so here you can see a waveform. I have compared two waveforms, that is, one is voltage waveform and the other one is a current waveform. And here you can see that they are having same frequency, then only we can compare them. So here you can see the 0 points of both the waveforms are at the same point, which means that both are in phase. And you can observe one more thing. You can see that the 0 points are coming together as well as their maximum points are also coming together, which means that they are going together, and we will call this phase difference as in phase. Let's go to the next one. Out of phase. Out of phase itself there are two types. One is lagging and the second one is leading. Okay, let's go through the first one, that is lagging. If two AC quantities of same frequency have different 0 points, and if the 0 point of one quantity appears after the 0 point of the reference AC quantity, then it is called as lagging. Okay, so how can we say? For example, in this case, the two quantities being compared are voltage and current. So, to understand the concept of lagging and leading, we should first select any one as the reference quantity. For this case, I am going to take V as a reference quantity. So, voltage waveform, that is, this waveform is the reference quantity here. Okay, and comparing with the reference quantity, we are talking about the other one, that is the current waveform. Okay, so here you can see the current waveform 0 point is coming after the voltage 0 point, which means it is coming after, and for such a case we will call current lags the voltage by an angle phi. Current lags the voltage by an angle phi. Okay, and you have to represent the waveforms like this. You have to draw and study how to represent it. And the equations we have already studied. V is equal to Vm sin omega t and I is equal to Im sin omega t minus phi. Why? Because it is lagging behind voltage waveform. Hope you understood lagging. Let's go for the next one, leading concept. Okay, so if two quantities of same frequency have different 0 points, again different 0 points, and if the 0 point of one quantity appears before the 0 quantity of the reference AC quantity, then we can call it as leading concept. So here also we are going to compare the two one, that is voltage and current waveform. And for understanding the leading and lagging concept, we need a reference waveform, and here we are selecting V as the reference, voltage as the reference. So comparing with the voltage waveform, we can talk about the current waveform. Here you can see that current waveform is having a 0 point here and the voltage waveform is having a 0 point here. You can see that the current waveform having a 0 point before the voltage is having the 0 point. Okay, so in this case we will be calling that, or we will say that current is actually leading the voltage. Current leads the voltage by an angle phi. And we have already studied how to represent each waveforms. V is equal to Vm sin omega t. I is equal to Im sin omega t plus phi. Why? Because it is 5 degrees leading the voltage. So this is how you have to represent the leading and lagging concept. So next we are moving into how to represent an AC quantity using a phasor. So normally for making a mathematical analysis, it is not easy to make additions, subtractions, everything using the waveforms like this. Time domain waveforms, it is not easier. Why? Because sometimes we will have to add a voltage waveform and a current waveform. Sometimes the voltage waveform will be like this and the current waveform will be a little bit lagging. So adding a quantity, adding two AC quantities is not so easy. So mathematically for addition, subtraction, multiplication, division, some different representation is needed. And for this purpose, we are going to study what is meant by a phasor. So representing an AC quantity using a phasor. A sinusoidal alternating quantity, or that means voltage or current, is represented by a line of definite length, which is rotating in a counterclockwise direction with an angular velocity of omega radians per second. Okay, we are going to represent the sinusoidal waveform using a line of definite length. Okay, and it is being rotated. It is being rotated in a counterclockwise direction with an angular velocity omega radians per second. Such an rotating vector is called as a phasor. So before going into how to represent it using a phasor, I'll be showing you what is meant by I operator, which you have already studied, just revising what is an I operator. So what is an I operator? You have studied in mathematics. What is an I operator? Any vector multiplied by an I operator, what happens? It rotates by, how much it rotates? It rotates by 90 degree in the counterclockwise direction. So it rotates by 90 degree in the counterclockwise direction. So if we are multiplying any AC quantity, any vector quantity by I, for example, A is a, here I have shown an example. If A is a quantity, okay, A is the quantity and or this is the vector. If I am multiplying with A, I am multiplying an I operator, that is I. What happens? It rotated by 90 degree in the counterclockwise direction. So what is a new form? IA will be taking this form. Okay. For next example is if I am multiplying with I square. So what happens? The A quantity rotated by 90 degree, then it is I into A. If I am again multiplying with I, what happens? It becomes I square into A. And now it has rotated by 180 degrees. So this waveform, this vector is shown here. Okay, then next one is if I am multiplying again with I, then what happens? It again rotates by 90 degree. Again rotates by 90 degrees, so it becomes I cube into A. Or we can also represent it as minus I into A. Why? Because I square is minus 1. Here also you can represent I square as minus 1, so it can be also represented as minus A. Okay, using this I operator only, we can study about what is phasor representation. So let us move into the phasor representation. So phasor representation of an AC quantity. So this one is the waveform which we have already studied. In the time domain, how can we draw the waveform? That we have already studied. Now we are going to represent this same AC quantity using a single line which is rotating actually. Okay, but rotation cannot be shown in the paper, but still it is a, you have to imagine that this is a phase, this is a vector which is actually rotating. Okay, so let us go through how it is being represented. So you can first go through, this is the phasor representation. This is the phasor representation and this is actually the phasor representation of this quantity, that is voltage. Okay, now how it is being done. First you note the axis. This is the 0 axis. This is the J or I axis. This one is the I square axis. This one is the I cube axis. I have mentioned it as J. It is actually I. Both can be taken. So 0 axis, J axis, I axis, I square, I cube. Okay. Now if the quantity is starting from a 0 position, then you can mention that this phasor should be starting from the 0 axis. Okay. If another quantity which is starting from this 0 point by after an angle 5 degree. Okay. After an angle 5 degree, if it is being started, then actually you have to represent it like this. Okay, so this is how you have to mention this one. And I'll show you what is being done. For example, only for this waveform, just go through the phasor representation. If this voltage waveform is at 0 position, then the phasor is actually at this position. Okay, now if the quantity is always changing its value, if it has reached at this point. Okay, for example, if I am taking this value as 45 degree, that means pi by 4. Okay, if I am taking this one as pi by 4, it is at pi by 4, the angle is at pi by 4. Then what happens is this one will have rotated by an angle 45 degrees. Now the phasor will be at this position. Okay, now again, if this one reaches here, okay, then which means it is the maximum value which it can obtain. And what is the angle here? You can see that the angle at this point is pi by 2. Then what will have been happened on this phasor side? This phasor will have rotated by an angle, how much? 90 degree and it might have been reached at this point. So what happens along with this movement or along with the change in the magnitude here, the phasor will be starting its rotation like this. Okay, and similarly in a counterclockwise direction it will be moving, and the value of that vector will be, that magnitude of the vector will be same as this maximum value. That is why I have drawn like this. Okay, so that is what how we can represent it for an AC quantity. For getting some more clear idea about how to represent the phasor for two AC quantities, we are going to study the next topic, phasor representation for two AC quantities. So we already studied what is the concept of in phase, then leading and lagging. Okay, using that same concepts we are going to study how to represent the same concept in a phasor diagram. Okay, so let us go through how to represent it. Let's go for the first one, that is in phase concept. So this waveform we have already studied. These equations also are clear for you. Now how can we represent this one into a phasor? So you can see here I have not drawn any circle here, how it is being rotated, what are the axes, nothing is mentioned here. I am just showing you how to draw the phasor. Okay, so the voltage phasor is actually starting from its 0 position. So this can be drawn like the previous case, for which I explained what is phasor diagram, which means you have to draw on the 0 axis. So you have to draw on this 0 axis. This is the 0 axis. So you have to draw it on the 0 axis. Why? Because it is starting from the 0th position. Now what about the current I? I is having a little bit less magnitude. Okay, but it is also starting from the 0 position. So you have to mention I as here, but the magnitude is a little bit less. So we will be representing the magnitude less than that of the voltage one. Okay, and this is how we have to mention the draw the phasor diagram of voltage and current, because both of them are starting from the same 0 point. So if you are having good imagination power, you can think that this both will be together making a rotation like this, while this magnitude is changing like this. So both of them are actually moving together. Okay, this concept should be clear. In a phasor diagram, this both will be rotating together. Let us move on to the second and third concept, that is lag and lead, and how can we represent it using the phasor. So here you can see voltage phasor. This is the current, voltage waveform, and this one is the current waveform. Now representing it in phasor diagram, how can we represent? Voltage waveform is starting already from a 0 position. Okay. Now what about the current waveform? So this one is clear for you, I hope. The next one is current. Current, you can see that after 5 degrees only it will reach the 0. After 5 degree only it will be reaching the 0 position, which means the I should be represented like this. What does it mean? After 5 degree of rotation, it is always rotating in a counterclockwise direction. So after a 5 degree rotation only, it will reach the actual 0 position, 0 axis. Okay, so that is meant by how to represent the phasor in a lagging concept. And the equations are almost clear for you. I is equal to Im sin omega t minus phi and V is equal to Vm sin omega t. So this is how you have to mention or draw the lagging phasor. We are not drawing any circle here. It is just an imagination. You have to, okay, now how can we think about this voltage and current phasors? They both will be together rotating. Okay, together rotating with always with a phase difference of phi. Okay, so this one together they will be rotating, but always there will be a phase difference between them as phi. We can see, we will just imagine that this voltage will be running first, then behind that I will be going behind voltage. Always there will be a small difference of phi between them, and they are rotating in a counterclockwise direction. Let's move on to the next one, that is the leading concept. And in the leading concept, you can see here, this is the voltage waveform. Okay, this is the voltage waveform and this one is the current waveform. This one is the current waveform. So how can we represent it? You can see the voltage waveform is already starting from the 0 axis. So we will be representing it on the 0 axis. This is the voltage phasor. Next comes the current phasor. You can see that the current phasor you can see that it has already reached its 0 position 5 degree before. So before 5 degree it was on the 0 axis, then only it moved and reached at this point. Okay, so here you can represent the current phasor like this. Why? Because before 5 degree, before it is moving in a counterclockwise direction. Before 5 degree it was on the 0 axis. Before 5 degree it was already having the 0 value. So for representing this, we will be representing in this manner. That is, I will be mentioned as it is ahead. It is before the voltage. So this is how you have to mention it. V is equal to Vm sin omega t. I is equal to Im sin omega t plus phi. Hope you understood the concepts of phase difference and everything, phasor diagram. Thank you everyone. Study well. Hope you understood.